variance controller, because if you see, we'll see later on, there are many other reasons why I selected this one. This is the basis for developing future adaptive controllers, these things. Let me tell you a story behind this. This controller was developed in 1970s, 73 mainly, when the Automatica paper came up. The guy is Carl Ostrom from Sweden. So he was assigned a task of the paper plant. In the paper industry, what they do, they want the thickness of the paper should be uniform. There should not be a non-uniform in the thickness. Okay? That means the variations around the thickness should be as minimum as possible. Right? So they wanted that you design a controller which will minimize these variations. That is a Carl Ostrom. So Carl Ostrom, with one of his PhD students, they developed a controller called minimum variance controller. Okay. Later on, it was found that this is the fast predictive controller. If you see it, this is the fast predictive controller. Okay. And there are many things I will tell you here, which is the basis for understanding the entire adaptive control theory. Right. Yesterday I told you that while fitting any models, you must know exactly that why the hell you are fitting this model. Your fitting model is not a joke. It should not be considered as an intellectual exercise. If you are very clear that why you need a model, then you fit the model. I'm telling you, roughly speaking, I'll tell you, if you are given a set of data and you are almost expert, not fully expert, almost expert, not a layman, for unknown data, it will take at least 3 months' time to fit a model. See how much time it takes. You understand these things? It's not a joke, just put to, yesterday you did, you put it ARX model and fit it. No, it never works like that. Okay, linear system is fine. Non-linear system is standard data sets. It will at least take 3 months' time. With some, you have to be an expert, right? And people will just give you like that. Take a data set and fit a model, right? So I told you that you must know that what you want to do with the model, then you fit the model. Because you are designing model-based controllers. Minimum variance controller which you are going to study, it requires that the system must be represented by a Rmax model. You got my point? If the system is represented by a state space, minimum variance controller don't design. It requires that the system must be represented by this model. Clear? If the system is represented by different model, minimum variance controller don't apply it. Not that you cannot apply, but don't apply it. The minimum variance controller minimizes the variance of the output. Variance of the output means, say for example, the thickness of the paper has to be uniform. The variation should be as minimum as possible. Okay. We'll see many things here. See, this particular controller, it requires that system must be modeled by this one, right? It must be modeled as y of t yt is equal to z to the power minus k b by a ut plus c by a et. The system must be represented by this form. If the system model is different, then don't use the minimum variance controller. Now I am giving the concept here. This concept is extremely important, and that will carry forward for the generalized predictive controllers and many of our adaptive controllers which have been developed over the years. See the idea. Idea is very important. Carl Ostrom thought, why the variations occurs? There is a system, you are applying an input. The input is deterministic. Suppose the system has no problem, then why the output will have some variations? First question, it came to his mind. The industry tells me that you minimize the variations. The question is why the variations occurs? See, why variations occurs? Why variations in the output occur? First question. I have to minimize the variance, no doubt over that. Right? Why variations occurs? Then Carl Ostrom found the variations are due to the noise present in the system. Then he found out, see the questions, it is due to the noise present. If there is no noise, there will be no variations. Clear? The objective is to minimize the variations. The first thing, if there is no variation, what is the question of minimization? So now he questions that why the variations occurs. He found that the variations occurs because of the noise, right? Now let us do one thing. See the mathematics where it's coming from. He told if the noise is the bloody idiot, it is he who creates problem, let us eliminate it. Suppose in this classroom, in this room, there are some idiots sitting there and they are creating problem. Remove them. Remove them, then everything will be fine. Yes or no? Very simple answer. Then you found it is not possible to remove all the idiots present in the classroom. It is not possible. Mathematically, we will show it now. Just a minute. It is not possible. Suppose in this classroom there are 3 idiots are there who are creating problems. If I could have removed all the 3, then I will get not a minimum variance controller, I will get a 0 variance controller. Because 3 people are creating problem, remove 3, what you will get? 0. Variation should be 0. But he found out, mathematically we will show now, that it is not possible to completely found out who are those 3 idiots. Complete noise estimation is not possible. If the complete noise estimation is possible, my job is gone, Professor Virakumar's job is gone, Professor Amal's job is gone, because noise is keeping us alive. It's not possible to do it, right? So then what he did, he told, okay, let's do it. We cannot completely estimate the noise. Let us estimate the noise, whatever is possible. And first we will estimate the noise from the given information. From the given information, we will estimate the noise. Whatever we will estimate, we will remove them. Understand the concept? If we can estimate everything, you will get 0 variance, but not possible, right? So therefore, what he did, he took this model, he found this noise component is C by A. You see here, which is noise component? C by A, right? C by A. Now, he analyzed that what we can do, because this is the useless fellow. This component is the useless fellow. Let's see. Understand the concept now? Noise is the problem maker. Remove the noise. Ideal thing is completely estimate, remove it. But it's not possible. Let us do what we can do with the noise, and whatever we'll see. Minimum variance controller, let's see. y t, I'm again writing here, z to the power minus k b by a ut plus c by a et. Minimum variance controller essentially minimizes the predicted variance of the predicted output, y square t plus k. It minimizes the variance of the prediction k-step predicted output. Right? So what is yt plus k? Let us see. What is yt plus k? Yt is this one. So will be equal to b by a ut plus c by a e t plus k. Is there any problem understanding these few lines? You have to understand because I need it. Z to the power minus k, here you see z to the power this is z to the power minus k is there. So therefore yt plus k means this gone, right? So we got only b by a ut and c by a et is here. So it becomes et plus k, right? Now in this model, c is equal to 1 plus c1 z to the power minus 1 plus c2. Why I am telling these things? I am coming to this point. C2 z to the power minus 2 plus cnc z to the power minus nc, and a is equal to 1 plus a1 z to the power minus 1 plus a2 z to the power minus 2 plus a and a z to the power minus na. Right? So which is the component which is creating problem? C by a et plus k, right? Now let us see what is C by A. What is C by A? Okay? C by A, this is the only thing you have to understand. Nothing else. Other things are straightforward. Now let us do one thing. Let us assume, suppose this is 1 plus A1 z to the power minus 1 plus 1 plus C1 z to the power minus 1. Simple. C by A, let us assume 1 plus A1 z to the power minus 1 by 1 plus C1 z to the power minus 1. So let us do one thing. Go to school now. Let us divide it. Now let's see. 1 plus A1 z to the power minus 1 divided by 1 plus C1 z to the power minus 1. I'm just doing few steps, right? So the first, sorry. What is that? 1 plus A1 z to the power minus 1. First is 1. So this is 1 plus C1 z to the power minus 1. Subtract it. This will be A1, sorry, 1 plus C, okay. So 1 plus this. That's right. You are correct. You are correct. You are correct. 1 plus C1. Okay, let me go to the other side. Yeah, that's right. Thank you. 1 plus C1 z to the power minus 1 by 1 plus A1 z to the power minus 1. Only these things please remember now. Let's do it. This one I will take little time. I put 1 here, so I get 1 plus A1 z to the power minus 1. 1 minus 1 cancel. This is C1 minus A1 z to the power minus 1. Clear? Now let us assume, give it a name as alpha 1 z to the power minus 1. Just to, okay. So now I will put alpha 1 z to the power minus 1 So this becomes alpha 1. This becomes alpha 1 z to the power minus 1 plus alpha 1 a1 z to the power minus 2. Yes or no? Right? So if you again subtract, then you will get minus alpha 1 a1 z to the power minus 2. Right? Let us assume this is equal to alpha 2 z to the power minus 2. Right? Then you put it alpha 2 z to the power minus 2. If you do like this C by A polynomial will become an infinite series. That is the key. The key is the C by A polynomial will become an infinite series. That is C by A. If you do like this, I am not interested for this which value, I am not interested for that. That is called 1 plus alpha 1 z to the power minus 1 plus alpha 2 z to the power minus 2 plus up to something like this. You see, the C by A, if you do this particular division, it will be infinite series. It will be infinite series. Just telling one thing here, a simple division polynomial 1 plus c1 z to the power minus 1 by 1 plus a1 z to the power minus 1. How many parameters are there? 1 plus c1 z to the power minus 1 by 1 plus a1 z to the power minus 1. How many parameters? 2 parameters, right? That can be expanded into an infinite series. Do you know what is the meaning of that? A finite impulse response having almost infinite number of terms can be modeled by only 2 terms by a polynomial. See here, this entire thing can be approximated by only 2 terms, right? I think Steve Billings could found out this particular thing. Then he got a couple of students who was working on the rational model identification using this idea. Okay, I'm not coming to that. So C by A polynomial is an infinite degree, infinite series now. Then C by A ET plus K, because that is the idiot. Who is the idiot? Creating problem. C by A ET plus K. Now see this expression here. C by A ET plus K is equal to, if I multiply it here, I will get ET plus K, alpha 1 ET plus K minus 1, alpha 2 ET plus K minus 2, alpha K minus 1 ET plus 1, alpha K ET alpha K plus 1 ET minus 1 and subsequently, right? Do you see anything here? See where I am coming from. Variations occur because of the presence of the noise. Let us analyze the noise term. By analyzing this noise term, he found this noise polynomial is an infinite series. He is at a time t, you are at time t, right? Now if you are at time t, whatever is happening at time t and before, you know it, right? What will happen in future, you do not know it, right? Now tell me in this expression, which terms you know and which terms you do not know? Not known. Et plus 1, Et plus 2, Et plus 3, you see? Alpha K plus 2, Et plus 2, alpha K plus 2. Whereas these terms you do not know, these terms are known. You see here? These are known. Or even EAT also this is known. Oh, dear. Why this is known because this depends on the past values, right? And this one, alpha k minus 1, ET plus 1. Do you know ET plus 1? You are at time t. ET plus 1 is not known. This is ET plus 2. Previous one is ET plus 2, right? Similarly, ET plus k. You do not know. Right? So what do you know? You know the past values. Okay? So this is the idea. So what he did, he analyzed the noise storm and split it into two parts. Which part he can predict, which part cannot be predicted. Right? That part which he will predict, remove it. So here, this particular part will always remain because it cannot be predicted, right? You cannot remove it. This will always remain. This will always remain. This will always remain. It cannot be predicted because this depends on the future values, right? So who will do it? This is the concept. Concept is clear or not? Concept is clear. Noise is creating nonsense. Predict the noise, and we found by analysis that the entire component, part of that we can know, part of that we cannot know, right? That part which you will know, remove it, right? Exactly the same thing. This is the mathematics. Another way of explaining is the C by A polynomial, I am not giving detail, is equal to F plus Z to the power minus K into G by A. So this one, this part is the first part which cannot be predicted. C by A is equal to F plus Z to the power minus K G by A. What I did it here this expression, this one, right? So you will find in adaptive control, in generalized predictive control, if you go, you are academics, you will go there, you will find this statement. Consider the Diophantine identity, C by A is equal to F plus Z to the power minus K G by A. This is the first statement. Adaptive control book, you go, generalized predictive controller, they will first tell, consider the Diophantine identity, C by A is equal to F plus Z to the power minus K G by A. When I started doing my masters, I thought, where the hell this identity is coming? Why it is coming? What is its significance? Actually, the significance is C by A is associated with the noise storm. So let us, any polynomial C by A can be split into two parts. One is F plus Z to the power minus K G by A. Okay? This F is the first term, few terms you see always remain. F is a remain. Okay, this one. And this is possible to show. This identity, I'm just coming here. Just a minute. This identity has been derived from the Aryabhatta algorithm. Indian mathematician, 450 BC. Okay? This Britishers, it is all recorded, I am not bothered. Let the people listen. The people of Western people, they did not credit Aryabhatta. They take it is Diophantine equation. Actually, it's not Diophantine identity. It has been developed by the Aryabhatta identity, right? It's all there now. If you go to Google and you go to ChatGPT, you can also find out the Aryabhatta algorithm, right? Aryabhatta found out, Diophantine found out later on, Then another person, his name is Bejout. The same thing he found out independently, Bejout identity. What this identity is doing now, this identity is being used by Carl Ostrom. He took C by A, split it into two parts. One part and another part, right? It is possible. Show it. It's identity, right? See, this part. C by A is equal to F plus Z to the power minus K G by A. Right? Now what he did, after splitting it, where the definition is F and G is there, right? Now you will find, if you put it, you will find, I am not doing the mathematics, y cap t plus k is equal to bf by c ut, that is mathematical you can find out, plus g by c yt, right? Yt plus k is equal to this one plus this one. You see the output has got two parts now. One is the predictable part, another is the unpredictable part, right? The predictable part consists of the actual dynamics plus small amount of noise part, because you cannot completely predict the noise, right? So this part and this yt, this is mathematical simple algebra. Now what he did, he want to minimize y. Now tell me, yt plus k is equal to bf by c ut plus g by c yt plus unpredictable part, right? I want to make yt plus k as minimum as possible. As minimum, ideally I should make it 0. But I cannot make it 0 because it has got two components. I have no control over f et plus k. I cannot do anything. So I can only do by selecting u, because u is under my control, the control input. I can only select, make this particular part what? 0. I can make this particular part 0, right? So which u will make it 0? If I make it u is equal to minus bf by gc, sorry, minus g by bf, see, if I make u is equal to minus g by bf yt, then this particular part will become 0. Right? So what Carl Ostrom did, you see, I'm just giving the concept, I'm not going into detail into the theory. It is the noise which creates problem. So let us analyze the noise. He found that noise cannot be predicted completely. We can predict part of the noise, and other part we have to bear with that. We cannot do anything, right? So what he did, whatever part he predicts, okay? So this particular part, you see, so he made that particular part 0. He made that particular part 0. So therefore, and if you do these things, you cannot do it these things, the output y will f et plus k will always remain output. E is the noise, f is a polynomial, so that particular part will always remain. I will give one interesting thing to explain these things. When the minimum variance control came, if you are implementing minimum variance controller, first thing implementing a minimum variance controller, assuming 0 noise, is a complete foolishness. First thing. If you are assuming there is no noise and you are implementing a minimum variance controller, that means you are the fool, the third grade fool. You are completely useless. Okay, first thing. Then I have seen in some of the power system journal, during those times when there is only one part, power apparatus and systems. Now it has been split. Some people, they will design a minimum variance controller and they will show that after sudden short circuit, the delta angle became like this, you see, something like that. Time. Minimum variance controller performance. Minimum variance performance of the minimum variance controller for a sudden short circuit in a transmission line shows like this. Paper get published in power operation systems. The person who has reviewed it and person who has done that particular research, their knowledge on the control theory is not zero but negative. Because the controller is the minimum variance controller. It is not a zero variance controller. So minimum variance controller, there must be at least some variations in the output. You cannot avoid it. The true thing is, if it is a minimum variance controller, the output, at least in this case, you see here, there will be some sort of fixed. F E T plus K will always be there. You cannot eliminate it. What I point? You cannot eliminate it because the theory says the output variance will be F into E T plus K, right? You understand not understanding the control theory, then how he got it? The student may not have included any noise, so therefore he got it. If there is no noise, then what is the point of minimum variance? If there is no noise, why you are implementing a minimum variance controller? As academics, you must be very careful in this case. If the problem is faulty, problem formulation is faulty, there is no noise, you are implementing a minimum variance controller. U is equal to minus G by BF, because it is there. You got my point? So minimum variance controller means the output will have some variance. And the important point is, the noise component C by A polynomial can be split into two parts. One part you can predict, another part you cannot predict. What my point? Now, any questions until this point? See the concept here. If the concept is clear, that the minimum variance controller, so if you are doing it, so you will find later on, whenever you design any controller on the discrete parametric model, any book you go now, textbook, what they will do, they will say consider the Diophantine identity and they will use similar type of identity, right? What it does, it splits into two parts. Okay, this one here. Okay, and then the analysis follows. So some part they will predict, some part they will not predict. And as an Indian academics, I must tell you, just replace that Diophantine identity, or you can combine together, you write down Aryabhata identity, okay? Diophantine, in my lecture handout, I give it Aryabhata identity, there is no problem, okay? So, this is the Aryabhata identity, or Diophantine identity, or Bézout identity. Three people have done it, okay? This controller, you see, ut is equal to minus G by Bf yt. Do you have any knowledge that this controller will be unstable if the B polynomial, if B polynomial has got any zero outside the unit circle, because discrete system, this will become unstable. Yes or no? Because minus G by Bf, B is in the denominator, right? So this is not suitable for non-minimum phase systems. Non-minimum phase systems not suitable. Not suitable. Because doctors are there to treat the patients. If doctor himself becomes a patient, then becomes a problem. What I point? So similarly, the controller is there to control the system. If the controller itself becomes unstable, then what will happen? If the B polynomial has got zeros outside the unit circle, it is in the denominator, right? Non-minimum phase systems, you know non-minimum phase systems, right? Non-minimum phase system means initially the output will go in the other direction. Okay. I'm giving a practical. My son always says, my dad is a clear example of non-minimum phase systems. Most of the father, they behave non-minimum phase towards their children. I'll tell you, I'm proving now. Anything your child will come and tell, initially you will say, no, you cannot do it. He will say, I want to go to the shopping mall. No, you cannot go. Then afterwards, you see, initially, no. Then afterwards, after some time, then some situation comes, your wife says, okay, he is telling and let's go. Then you will. You see, initial response is, see here. See, I'm plotting the response. Oh dear, why this is happening? Initially, the response will be negative. Whatever you say, initially no. Your boss, anywhere, everywhere the boss, they will do the same thing. You to ask him, I want a conference leave. No, why you will go to a conference? Don't go there. Then after some time, you convince them, then they will say, right? There are several examples of non-minimum phase systems, right? A child, toddler is started working, okay? Non-minimum phase system. You ask him, you come forward, you walk. Immediately, instead of coming forward, he will go backward, 1 or 2 steps backward, then forward, right? So there are so many examples. So the minimum variance controller is not suitable for non-minimum phase systems, right? These things were developed by Carl Ostrom. See the concept. Then David Clark, who is the father of the generalized predictive controller, he was in Oxford. He has got a student called Peter Gothrop. 1975 proceedings IEEE, they found out another paper, Clark-Gothrop type controller. Just based on this criteria, David Clark and Peter Gothrop. Okay. They developed, as well as another guy in EMIST. I know all these people, they used to come to our university during that time, the Steve Billings friends. Peter Wollsted, P. Wollsted. He has written a book on self-tuning controller, very big book, widely published. They developed a generalized minimum variance controller, which I'm going to do, and you will do the assignment today. Generalized minimum variance controller, they generalize it. And what is that? I'm just giving the concept. Instead of minimizing the variance of output, they try to minimize the variance of a function phi t plus k, not of yt plus k, which is a function of output, input, and the set point. 3 things. This is the things which David Clark did it with Peter Gothrop. Okay? Instead of yt plus k, they did it. They formulated a generalized function which has got y, q, and r. It is same as the minimum variance controller. If you take q is equal to 0 and r is equal to 0 and p is equal to 1. Okay, but they made it generalized. Now see the point of what I'm trying to tell you here, the concept here. Who is the idiot here? Noise. Now this phi t plus k, simple algebra will say you, this is pb by qa ut. The noise component is not c by a, pc by a, right? Noise component is pc by a. This is the idiot who is creating problem, right? Who is creating these variations? Noise component. Now in this formulation, which is the noise component? PC by A. Now you see the formulation, straightforward. You can tell to your students, see here. Consider the identity PC by A is equal to E plus Z to the power minus KG by A. Analyze the noise component. Earlier, what we are analyzing? C by A is equal to F plus Z to the power minus KG by A, right? Because C by A is the noise component. Now, which is the noise component? PC by A. PC by A. So now we analyze that one. You split it. PC by A, some different name here. E plus Z to the power minus K G by A. This G and that G is different, right? Split it. Right? So similarly, when David Clark developed the generalized predictive controller, his noise component is different. His noise component is different. But the same thing, he took that particular component, split it into two parts using the Arrhenius identity. Okay, and then other things are algebra, simple algebra. Just put it, substitute these things, that thing, you will get a solution. See the idea here. So when we were students, we were thinking, where this identity is coming, what it is doing. It's very difficult for the teacher who was teaching that to understand also. So we understood these things, that this essentially split the noise into two components, okay, and use it for this purpose. This generalized minimum variance controller is applicable for non-minimum phase systems. It can not only it can minimize the variance, it also can solve a tracking problem. It can track a reference. Minimum variance cannot track. Minimum variance controller actually is not a minimum variance controller. It is a minimum variance regulator. But this one is a tracking controller. By using the WT reference, it can track the reference. Right? Many types of control strategies, PI controller, PID controllers, can be designed by suitable selection of Q polynomial. So these are the ways. This generalized minimum variance controller has got so many advantages, right? Huh? No, this one will general GMB will be applicable because you have got the freedom in selecting so many parameters P, Q, R. So adjust, you can do it. Now the control law will be UT is equal to minus GY minus SW by F, where it is defined F is equal to BE plus QC and H is equal to minus RC, right? Yeah. Which one? Now I'm coming to that point here. UT is equal to the number 5, please remember here, because I will discuss these things in the assignment today. This is the extremely important point here. UT is equal to minus GY minus SW by F. What is F? Is equal to BE plus QC, right? F is equal to, just only this thing you try to understand now, then I will tell you. F is equal to BE plus QC, right? Now tell me, what is Q by definition? Q is equal to Q0 plus Q1 Z to the power minus 1 until the something QNQ Z to the power minus NQ, this Q by definition. C polynomial is equal to 1 plus C1 Z to the power minus 1 plus CNC Z to the power minus NC, right? That is by definition, right? So forget about that higher terms. So QC, if I multiply QC, okay, there will be one term Q0 plus something. You see, it doesn't matter, I'm not interested. The first term will have Q0 because Q0 is multiplied by 1, right? Clear? Without any power. Did you see it? Q is this one, Q is. Now let us go to BE. B because they are added. B is equal to B0 plus B1 z to the power minus 1, blah, blah, blah. C is equal to 1 plus C1 z to the power minus 1. Now, if I multiply B into C, what is the first term? B0. B0. Now, F polynomial, let's see now. F polynomial is equal to F0 in general structure is F0 plus F1 z to the power minus 1 like this. Now, can you just tell me what is F0? F0 is equal to B0 plus Q0. Do you understand? F0 is equal to B0. This point is very important because this is necessary for our controller design now. F0 component consists of B0 plus Q0. Q0 is the component which you are controlling. That is the tuning parameter. You are tuning it. You know it. What you do not know, the system parameter B0. Are you convinced that F is equal to BE plus QC? F has got this structure. Therefore, F0 will have B0 plus Q0. Clear? This point please try to understand. This is the only point you have to understand. F0 is equal to B0 plus Q0. Clear? Out of which B0 is not known, Q0 is you are giving. So, that is under your control. That is under your control. Right? Now, you see here, I am not entering those things. See these things you will do it today. In adaptive controller, what you do, just like in the state feedback controller, U is equal to minus Kx. If X is not known, you estimate X and put that estimate in the controller, right? Instead of U is equal to minus Kx, you do it minus K into X cap, right? Now here in adaptive controller, what you do, you get the measurement online. You estimate the system parameters and put that estimation in the system. How it becomes adaptive? So as the data comes online, you estimate it and use that estimated things here, right? So the step number 1 is you get the output. You know what is P, Q and R, that you know, that you give. Then you formulate this one, phi t is equal to P y t plus Q u t minus K minus R w. W is the set point. Then you estimate F cap, G cap and H cap using this equation. This itself will take around half an hour to explain actually how to estimate these things. Anyhow, now F cap, F has got the structure F0 plus F1 z to the power minus 1 plus F2 z to the power minus 2. I am just doing 2 things. Okay, first term let us see. So phi t is equal to F0 u t minus k plus F1 u t minus k minus 1 plus f2 ut minus k minus 2. Any problem? The first term, f cap ut t minus k. Suppose f is equal to f0 plus f1 z0 minus 1 plus f2 z0 minus 2. So the first term will be, I am not using that, means phi t is equal to f cap f ut minus k. Is it f0 ut minus k plus f1 ut minus k minus 1 plus f2 ut minus k minus 2, right? That is equal to, here you see, what is f0? F0 component has two components, B0 plus Q0, right? So you write down, this is Q0 ut minus k plus B0 ut minus k plus F1 ut minus k minus 1, like this, right? Now out of which this one you know, your Q0 you are giving. So bring it to the other side. You will do it today, you will know it. So the estimation equation will be phi t minus Q0 ut minus k. This is in the right hand side is equal to the other things. You have to estimate these things. Okay. See here. While estimating the control parameters in step 2, use the estimation equation as this one. It requires, if you do not have a background, it requires little time actually to understand. So I have given the program, you will do it today. I am not telling that you can understand everything unless you do it before. Important thing you must carry forward is that a Diophantine equation which you are being used to do these things, essentially split it into two parts, noise component which is predictable and another is not predictable. That is the key point. Other things are simple algebra. You will see it. Once you do that thing, the other things are fine. So we'll take a break. I think, see, here everything is here. What is the power and everything, all these things are given here. We teach 1 week course, 1 week for this generalized minimum controller in the, so difficult to, but I am telling you the important point here. And the program is, I think I have given the program in the, here itself I have given the program. At the end is there, yes. So at the end the program is there. See, F0 is equal to this one. This one, yeah, minimum variance controller is a very simple controller, so it can do it. Yeah, the only problem here is model predictive controller which we are going to study now. Model predictive controller should not be used by the usual electrical engineers, because MPC has been designed especially for chemical process plants. Nowadays people are using MPC. MPC is computationally very expensive computations. And whenever a simple PID controller can do the job, why MPC? Model predictive controller is a hell. This one is also one sort of predictive controller, because you are doing yt plus k, you predict it. You are not minimizing the variance of the output, you are minimizing the variance of the predicted output, the theorem. Okay. This is also predictive control. Okay. David Clark developed GPC based on this thing, different type of model, but similar type model. Similar control horizon, all these things. But I am telling you, MPC, our students are doing it because now we have to publish papers. We have to live with that. It's the situation like this. If you don't do it, we have to deal with that. But sometimes, as I told you, I don't like neural network, but I myself has published many papers in neural network. We can do it. We can't help it. The student will say, I want to work in machine learning, artificial intelligence. I said, you should have a natural intelligence first before doing the artificial intelligence. Huh? Yeah, people don't think about that thing, right? Every time 100% students will ask, what are the poles of a system, control theorist? Poles of a system where the transfer function becomes infinity. I ask, where the hell you are getting transfer function? Where the hell the transfer? I am asking questions to you, what are the poles of a system? You are telling me where the transfer function becomes infinity, where the transfer function term came into picture. You got a point? So your understanding should be clear that the poles has nothing to do with this transfer function, because transfer function do not exist. First thing is the models, the differential equation models, transfer function, what you say, that do not exist. On the back of the mind, you should have that thing, that what you are doing is a mathematical abstraction. So that concept, our students now know. Our students now know. I told them that in future, if someone asks you what are the poles and zeros, so they are clear. At least that much they are clear now. So I want that you should also tell them the characteristic modes and what are zeros. You don't need the concept of poles and zeros, and you will talk all these nonsense things. What's the point? Sliding mode based, MPC based controller. There is one student who has Journal of Energy Storage, who published the paper now. There is a student from China, Peng Jing. Peng Jing, we have published a paper and just sent a mail when I was in Goa. Dr. Swai, it was accepted in the energy storage. I told Jing, sliding mode controller with the MPC. No, I will do some multi-agent also attached. I don't know. For God's sake, don't do it. Don't do it. Multi-agent, sliding mode, MPC, observer. How many things you are combining in a power system problem? Everybody is doing it. We can't help it. We can't help it. Okay. Similarly, I'll tell you another important thing before I go to the MPC. We'll have a cup of tea now. Kalman filter, you see, Professor Veera Kumar knew it better than me. Kalman filter, you go to your academics, you find the students. Kalman filter, first you predict, then you take the measurement, then you correct that. Prediction, measurement, then correction. 3 steps. That is going to the brain of the students, it becomes difficult. You say, what is this? X cap, K cap plus, X cap minus. What is that? The 3 steps procedure. You predict, then you take the measurement, and then you correct it. 3 steps. So unless you know the fundamental things there, how people will do Kalman filter, extended Kalman filter, uncertain Kalman filter, particle filter, all those things. I have done it. I myself have done it. But I am saying Kalman filter is very powerful. How many people have studied, seen that paper, 1958, engineering journal, where the first paper of the Kalman came, 3-4 pages paper, 1958. ASME journal of engineering. Nobody. You got a point? So the things happen. We have to deal with that. We have to work. Although we know this is useless, we have to do it. Yeah. We will not eliminate non-minimum phase. Yeah, yes. I think non-minimum phase systems are little difficult to control, but I think most of the controllers, MPC and all these things can tackle the non-minimum phase. They can tackle. No, PID can control. Non-minimum phase, see, non-minimum phase. Yeah, I am giving the analogy here. The child is mischievous, but whenever he becomes young, then he will be, he becomes better. No, pole zero cancellation type controller should not be used under any circumstances. Under any circumstances, do not use any pole zero cancellation controller, because it has nothing to do with the system. Because your poles and zeros you are defining on based on a transfer function. The transfer function model has got poles and zeros, you see it. But that is imperfections must be there. So don't do it. Pole zero cancellations. Pole zero cancellation, we don't do it. And I will always advise don't do that pole zero cancellations. Non-manifest system little bit, it requires little bit more control effort, nothing else. Because initially he is not obeying you, but finally it will obey. I never seen any difficulty. Yeah. Tell me what the zero location says. Right hand side, yeah. No. Yes, that's good question. No, there are controllers, pole zero placement controllers. It is there. It is the pole zero placement controllers. Sometimes I was teaching that, not pole placement, pole zero placement. Pole zero placement. We'll see.